everyone, and welcome to CW Trending Composites World's video podcast. We're going to talk about thermoplastics and thermoplastic composites today. I have three guests, and they're all from Solvay. So before we get started, I'm just going to ask our guests to introduce themselves, and let's go ahead and start with you, Trevor.
Yes, Trevor Mcrae. I'm the North America Applications Development Manager for thermoplastic, carbon fiber and glass fiber reinforced composites. Originally started at Boeing for 21 years and then on to a supplier. And now I'm happy to be continuing with the materials use at Solvay.
Great. And you have some great parts behind you there, so maybe we can talk about those. Johannes, why don't you introduce yourself?
Yeah, hello, Johannes Seiber. I'm currently a thermoplastic application engineering manager in Europe, coordinating within the thermoplastic composite platform in Solvay. First of all, engagement with the customers, but also the technology roadmap development together with our application center. We have a material science application center in Brussels, and then coordinate the activities with stakeholders, external technology suppliers, customers. From a background, come originally from aerospace engineering and worked then for many years in automation of composites. That means fiber placement before 5 years ago joining Solvay, and with some years in thermosets now, really since 2019, working on thermoplastics composites in our team.
Great, thank you. And Jim, why don't you introduce yourself?
I'm Jim Pratt. I'm a senior tech fellow in the thermoplastic composite platform and lead scientist for product development. And I've been working on thermoplastic composites since 1985. So I'm sort of the old man of the group and one with a lot of histories and stories. So certainly great to be a part of this today.
That's great. So these materials are not new to you, so that's interesting. All right, I'd like to set a baseline here and just find out, just for our audience, explain briefly what are the thermoplastic products that Solvay offers to the market, and which resin types are offered and which formats. I think just to give us a basic understanding of what kind of materials we're talking about today.
So today, Solvay primarily supplies, the bulk of it is unidirectional tape, with a few select fabric product forms for a few customers. The resin systems that we've identified and have initially gone out commercial with, excuse me a second, sorry, is polyphenylthalamide, PPA, PVDF, PPS, PEEK, PECT, and PEI.
Okay.
And again, all of these can be provided in unidirectional tape form with both carbon and glass, for the exception of PVDF, which is only offered in carbon.
Okay. And what is the maximum width of these tapes?
Today, the maximum width for the APC product line, which is the PEEK, the PECT, and the PEI, is 12 inches wide or 305 millimeters wide. For the Evolite products, which is going to be the PVDF, the PPS, and the PPA, we recently announced a capacity increase of putting a plant in Piedmont. And so the tapes for those will eventually be 24 inches wide.
Okay.
Today, presently, they're 6 inches.
Okay. There are lots of ways to apply thermoplastics to UD tapes. Can you walk us through the technologies that Solvay uses to do that?
We have two basic impregnation process. As I mentioned, we have our APC product line, which has been around since the 1980s. It is a hot melt process. It has some very unique characteristics with the tape that some of our customers, or a lot of our customers, are actually taking advantage of it in stamp forming and press forming. And then the other one is the aqueous slurry process. So that will be with our Evolite materials.
Okay. In which end markets is Solvay targeting its thermoplastics right now? Where do you see the greatest opportunity? Where's the activity?
Well, there's three basic core markets, but as we continue to work, that may expand. The three core markets are aerospace and defense, and that includes urban air mobility, where there is a lot of activity ongoing in that market space. There is the automotive sector, and then finally what we call the energy transition markets. So, which also has a lot of activity going into it. You have activity going into hydrogen, so tankage. Certainly in the oil and gas market, there's piping ongoing and other applications in that market segment. So I would say we have quite a bit of interest in each one of those segments. And as I mentioned, as time goes on, we're beginning to get inquiries for applications outside those three core markets, and we will evaluate whether we have the right product forms and products to be able to be successful in those.
So you feel pretty optimistic about thermoplastics use in pressure vessels for hydrogen storage?
Well, I think we're at the very beginning, and so we're reasonably, we think we have an approach and some products that could be, could fit that market. So we're a little bit optimistic at this point, but we're at the very beginning.
Yeah, it's definitely a young market and very exciting. You mentioned automotive, and I guess that could lead to my next question. I wanted to talk about overmolding. You know, for the purposes of our discussion here, how would you or Solvay define overmolding? You consider that injection molding on or around a continuous preform, or how do you define that? Just to give us some parameters here.
Yeah, I can cover that one. It's a very good question, actually. One where we had to learn ourselves internally first, having a common understanding and common knowledge. First of all, we had the special polymers colleagues coming from an injection molding perspective.
Right.
From a global market perspective, for sure, it's seen as overmolding onto anything. But in the thermoplastic composites platform, on this side, on the composites perspective, we definitely define it as structural overmolding in the first place, structural connection. That means really injection molding with full interface healing and full interface structural performance, and then onto both continuous composites but also long fiber composites. So LFT products can be also an insert which can be overmolded and functionalized with short fiber molding compounds. But yeah, then again, we see quite an ambiguity in terms of markets. If you take the classic composite markets, aerospace, urban air mobility, then you have the classic functionalization. That means taking a compound and injection overmolded just by functionalizing a classic composite structure. But then automotive, as you mentioned, automotive, there we really come more from the classic injection molding side, and overmolding is seen as local reinforcement, local improvement with composites, and the difference there is really then the highly functionalized, the highly directional use of composites with very wide range of product forms, very wide possibilities from rod stock to blanks, so not the classical aerial composites. And that makes it not very easy, not very straightforward to say what's overmolding. It's we see this by market, by technological approach, and from which direction you take it.
Is there an end market in particular that you feel like is strong there? I'm sorry, Trevor, I may have cut you off, but is there a particular end market that shows great promise there?
Trevor, do you want to add perhaps still to?
Well, I was just gonna say and reiterate. You know, classical, when we say overmolding, it's as if there's a composite there, and then we're injection overmolding onto the composite, which is kind of the classical way to look at it. But as Johannes was saying, you know, when you get into automotive, they're very familiar with injection molding, and it's as if the tape is introduced as just the reinforcement there. So I'd say, to your question, Jeff, that automotive, in my opinion, automotive is kind of the first place that's really keen on utilizing this. I think the tools to look at it from a structural standpoint in aerospace are a little bit lagging. The ability to put that all into a model and know what that part's going to do each time is a growing maturity level in aerospace. But I would say automotive is probably the first area. What do you think, Johannes?
Yeah, to be honest, I fully concur on that aspect. If you take the high performance thermoplastics, for sure, if you take overmolding from a broad range to the commodity plastics or engineering plastics, there might be different application spaces, but we see the strongest driver for sure from automotive in metal replacement, in metal replacement, the challenges on aluminum die cast parts is that you need a high performance compound or polymer first. And the classic injection molding compounds are not sufficient anymore in its performance to reach. And there we see a very strong drive. So on this local functionalization, but definitely with its challenges, that best use of composite, anisotropic use of composites, not just the classical organo sheet. But that's the stronger driver. We see surprising in the classic composite markets. It's the urban air mobility which probably brings the biggest potential if you especially not take flying taxis, but even the drone space. Drones, they need to be manufactured at such high rate in a very short time that overmolding with the requirements for aerospace, with the requirements of certification, etc., are really an interesting opportunity of functionalization being brought into these parts. So that's another area where we see strong development.
So the urban air mobility space, even if you apply thermoplastics, as you noted, Trevor, there's a modeling challenge, which I assume will exist in urban air mobility as it does in commercial aerospace. But maybe we have a longer runway there because it's still an evolving and maturing market. And what is your take on that?
Do you want to cover this?
For me, and then I'll hand it to Johannes. I feel like the urban air mobility space, because it's newer and a lot of the people involved are a little bit more open-minded for product forms, products, processes, the combination, like with injection overmolding. I think they're more apt to look into the way to model, simulate, and get what they need. I think traditional aerospace, it's just our own nature, it's psychology. Our comfort level is what we know. And so to be able to kind of crack that open and look at new and emerging things takes a little bit longer in that process to feel well with what was unknown but is now new technology.
Okay. Johannes, do you have anything to add to that?
Yeah, perhaps a good door opener could be in this space, coming from the smaller aircrafts, the transport aircrafts, etc., where certification needs are less, where it's easier to get them certified, and there then to prove the technology and to bring it to life quickly. Especially the ramp up and then the needs from the market are so high that this will be put into flying objects very quickly, and so we have probably a good learning curve.
So you mentioned ramp up and demand from this market. We hear different numbers from different people about what this market might look like. Can you give us a sense, based on what you're hearing, what your expectations are for this market in terms of either unit demand or how do you perceive the demand picture for this market?
It's a very good question.
Which one does want to take that one first? I'll give you my opinion on it. I think this is a new market, and they're going to have to go through the certification challenges, particularly for the manned vehicles. And so the numbers you're going to be talking about in the time frame is probably going to be a little bit longer than what everybody is hearing, and the numbers are going to be a little bit larger. but it's going to take time. And as time rolls, some of the large numbers we're hearing is approaching automotive level. And I think that's why thermoplastics somewhat resonate, because it's not necessarily at this beginning phase of getting certified and qualified, but it's the phase of industrializing and getting into the larger volumes. How do you meet rate production? And I think that's a strong point for thermoplastic composites.
So to put some numbers to this, I'll tell you what I've heard, and then maybe you can respond to that. So what we keep hearing is that between now and say 2025, 2026, there's not a UIM manufacturer who's probably going to exceed more than 1,000 units a year. And if you're under 1,000 units a year, you can, for the most part, rely on already qualified materials using already qualified processes, whether that's hand layup, AFP, but maybe probably autoclave cure. Once you get past that 1,000 unit per year threshold, you then are getting into rates and quantities where traditional materials aren't going to meet the need. And the window for that is looking like between 2026 and 2030, followed between 2030 and 25 with what some people have called like full industrialization, which is completely out of the autoclave, highly automated, repeatable, good process control, good in situ quality checking, and fairly high rates, up to maybe 10,000 per year, although I think when you're talking 15 years into the future, it really gets muddy. Is anything I just said, does anything I just said make sense? Does that resonate with you? Or do you feel like, Jim, like you just said, are we looking at a curve that's maybe even further out than, say, 2035? Are we looking at 2040?
I think it really depends on how long it's going to take for these to get the certification. And, you know, we're focused on the structure part of it, but you have to get into things like air traffic control and flying over, you know, suburban or urban areas. And I think that's just going to maybe take a little bit longer than people are anticipating. So I think once they can get clear of those hurdles and people begin accepting the technology, then I think the larger volumes will come, and they will probably come very quickly. Whether that's in the 2026 to 2030 timeframe, you know, your crystal ball is as good as mine or anybody else.
Okay.
And I also agree with what you said about a lot of companies were just trying to get off the ground, get their vehicle ready to flight test, whatnot. So they used the available technologies where they were comfortable with. And now they're realizing, you know, none of that supports our future rate plan. The concern there is when you go out and certify a vehicle out of a certain material set, knowing already that you're going to have to go back and replace that with, you know, that will be, I think, a bit of a challenge in the future that has not really been realized yet. They realize it's not going to make rate, and so we get a lot of discussions about thermoplastic structures and materials there. But that company needs to realize they're going to have to revisit a lot of things that may be painful because they've already certified a vehicle under different material set. But I think I think they realize we're having those conversations, and they've realized that they need something different to support rate. If they can bring that home before certification, then that's going to be a much easier process.
It's if we take the small aircraft, I was talking quite a bit about drones already. Even there, it's amazing to see how much relearning the classic aerospace tier ones, which are tasked right now to organize and get the manufacturing en route, how much learning and relearning they have to do to bring an automotive mindset for the thermoplastic rate capability in there. And that's a steep learning curve, which definitely where we see even for these small aircrafts with a lot less effort, the timeline slipping. So it's the 2025, 2026, I would have assumed that the transition is slightly later than that, even because it's this critical, the step over to thermoplastics is still a hard one.
Yeah, because even in the automotive supply chain, the qualification environment is not, there's no equivalent. So the qualification environment in aerospace is very different from what it is in automotive. And so when we talk about aerospace quality at automotive quantity, I mean, it sounds nice, but yeah, the differences can be pretty stark. So, okay. So I want to wrap up with overmolding. What kind of attributes or what kind of performance characteristics do injection overmolded thermoplastic parts provide that are most appealing to the customers you're talking to? What makes that a good solution for their problems or their challenges?
If I split again between these different markets of it, what we have talked earlier on about, is on the classic injection molded parts, or where the development comes from the injection molding side, stiffness and creep are probably the most critical aspects which the overmolding, which the composite insert brings, where dimensional tolerance is crucial. We see a lot of in automotive with electrification and e-motors, rotating parts, but even in urban air mobility, fast rotating parts, where there is injection molding possible, but where there's a concern around dimensional stability, electric motors, where the creep of the part is crucial, where the shape tolerance is crucial. Right. From the classic composite overmolding side, for sure, it's the functionalization. It is the ease of assembly, reducing the part number by integrating stiffness, but more importantly, even in mounting points, assembly points, reducing the assembling effort is probably the most critical aspect. We always talk about light rating. What's light rating is on all of these parts core in aerospace and in automotive. But in automotive, we repeatedly hear that light rating is no longer paid for. That's a necessity. Right. That's actually a necessity to reduce the amount of costly composite, the higher cost composite insert. Minimizing it brings light rating, but also drives down the cost. It's the rest, the TCO aspect and the rate capability, which really make the difference. It's not the light rating itself is not valorized anymore.
Okay. You mentioned rotating parts. Can you talk a little bit more about why creep and dimensional tolerance are so important for rotating parts?
If you take new electric motor concepts, so not the classical rotor stator concepts, but go into alternative motor for electric cars, you have fast rotating beyond 10,000 RPM rotating parts, where dimensional tolerance is key, where distance to magnets is key, where you have very tight tolerances, and because of these high rotational speeds and the need for acceleration and deceleration, the classic metallic components are not as interesting because they have high inertia. But especially in rotor stator combinations, in axle combinations, for example, the dimensional tolerance is key. And classic compounds, if you come from the injection molding side, under continuous loads, and high temperatures, which you have in electromotor, for example, you will see some creep aspects where classical compounds start creeping.
And I assume that because these are rotating parts, there's centrifugal forces at work, and you need to maintain some balance, mass balance. Otherwise, it could throw everything out of whack, right?
Exactly. It's a combination, and it's creep. The dimensional tolerance, what composite brings as well, is the reduced sensitivity to thermal expansion issues. If you take a classical injection molded part, as soon as you bring this up to 120 degrees C, as can be normal in electric motor applications, then suddenly they start deforming just by the compound expansion, especially if we see them in hybrid applications, which we are working on. So combined with metal parts. And there, the composite, the overmolding really can tailor it with the challenge of then designing it accordingly.
Okay. You mentioned that weight is not valorized, weight reduction is not valorized in automotive. Why is that? What are you hearing from your customers about why it's not cherished the way maybe we thought it was, or maybe the way it used to be?
If you take battery boxes, electrification battery boxes, you can with 2 more modules in there or 1 more module, you can easily compensate 10-20 kilo of weight increase. You can simply compensate, but what's the point is the space, the available space is a lot more critical, for example, for such battery boxes. So it's just one of the aspects where we can a lot more easily address the functionalization, the other aspects than just trying to sell it by lightweighting. We basically get very much the feedback. We are not paid for the access, or the lightweighting itself is not paid for. That's unnecessary. Yeah. It's just we need to be lighter in the first place. Cars get too heavy. Lighter is not something safe like in aerospace. That's just baseline, and you're not getting extra money just for being light in the first place. So we need to be always competing on metal solutions, aluminum for lower rates, steel for higher rates. And if you're more expensive, then it's just the costs are key and not so much the lightweighting aspect.
And by not paid for, maybe that extends to the customer environment. I don't imagine there are many customers who walk into an automotive dealer's showroom and ask for the lightest car available. Right. At least not the way airlines do.
It's for sure, lightweighting is still, it's the benefit in the end. We are doing the metal replacement in electric motor housings, etc., because they get lighter, because every gram counts. But then again, in this discussion with automotive tier ones, etc., we repeatedly hear that within these teams, this lightweighting in one area of the car is not accounted for by other teams. So it is just part for part, group for group, has a specific target which they need to meet. And everything better than that is not valorized as a whole, because it's just the team has a specific target. Other teams are not benefiting by being heavier because another team basically did some lightweighting. So that's a mindset, an organization aspect for sure as well in these companies, which we are fighting. But unfortunately, that's what we see then in terms of lightweighting.
Okay. So we've talked a little bit about the strengths or the benefits conveyed by overmolded parts. What are some of the bigger challenges associated with overmolding that our audience should be aware of?
Probably the biggest, if you go for structural overmolding, where we try for an interface, for a structural interface, for then the predictability and the performance of the interface in the first place. So having a design chain, having a simulation chain for predicting the mechanical performance, which is highly complex, given that you have a possible 1 or 2 shot approach, how you make your composite insert, impacted by the processing settings, the process window, the injection molding with its flow dependency, its geometrical dependency. So that's the biggest, but then directly followed definitely by design guidelines. You add a degree of freedom. We have a complex composite environment where we have a lot of flexibility with stackings, with product forms. We have an additional degree of freedom now added by having the compound with its different shapes, its different forms, its different ways of how to interact, from local ribs to aerial overmolding to local features. So the design guidelines, and for somebody like Solvay, for sure, material card generation. You have in injection molding, you have a vast range of product forms, of compounds. We have several product forms on the composite side, and every customer might choose a different optimized combination, and suddenly we need to be able to very quickly turn around material cards, characterization of the interface, the process hinting, etc. So that's additional.
I agree with that, and what he's saying for people that are looking across the spectrum of the different reinforced materials. Solvay has the compounds that work well with those, and like for instance, with the PEC material, you tend to like for overmolding a temperature differentiation there, so the PEEK overmolded material works well with that PEC material. That's the reinforced part of that. And so, like he's saying, the MSAC Center Material Resource Center that's in Belgium does a lot of this virtual engineering and these data card generation to be able to support that, so that our customers, beyond just receiving materials, have the ability to combine those and know what the effects are going to be.
All right. So as you just said, clearly Solvay is offering design help, design guidelines, material cards. But you also mentioned earlier, Trevor, the modeling side of this, which is a software issue, which must mean that you're also working with the CAD suppliers. I mean, how does that work? How do you take your knowledge about design for overmolding and convey that to a modeling environment that it has value and use to fabricators?
Yeah, I think that's a great question. I'm probably going to pass that to Johannes, because I bet he has better insight than I do into that, because that is exactly what the MSAC Center and virtual engineering helps with.
It's definitely a challenge. It's we have multiple activities engaging on the computational chains, so it is still a development need for the computational chain of the interface prediction, for example. So there's directly collaboration with software suppliers, but also if you take research centers such as TPRC and others, really adding here value by bringing it to wider attention routes. For our own team on the virtual engineering side, we also, we need right now, and that shows already complexity in this market, we need to bring composite experts, design for manufacturing experts, and injection molding experts together, have normally a cross-functional team engaging on overmolding opportunities, on new overmolding opportunities, and then have a strong need for a virtual engineering team coming in, bringing the topological optimization, the interface characterization and prediction, and then design for manufacturing from the processing side and application engineering side, to best use of product forms of the composite side, and the process limitations. It is right now a complex process, which is also coming back to the challenges what I was saying early on. For somebody not having this in place already is definitely something to work on. Hence, that's why Solvay has specifically a virtual engineering team, has an application engineering team working very cross-functionally to support right now industries, especially, for example, automotive.
I wonder, what would be the ultimate goal here in terms of modeling and designing for injection overmolding? Would you hope that every major CAD program out there has a module in it that provides the kind of data and the kind of capability and modeling that you need, or do you see that there are one or two who are really engaged with this and are working with you closely, and that you see there's promise and opportunity? What's the end game here?
From how I see it, I assume that there will be a strong link to the classic injection molding side. So we have MoldFlow, Moldex as simulation tools. An expansion on these platforms is very likely to have then expert tools. We see on specialty polymers injection molding application nowadays already that there's always a dedicated team engaging. It is not do it yourself and try and error. You have always an expert team trying to support customers, and customers working closely with material suppliers and end users to really to work through this challenge. But yeah, in terms of software, I expect that it's specialized platforms a specific number primarily coming from the injection molding side.
Okay. I want to revisit. We talked earlier about qualification for aerospace and for urban air mobility, and I wanted to revisit that a little bit. The qualification environment is a fairly complex one. We've got some qualification work being done at organizations like NCAMP at Wichita State University. We have qualification being done by OEMs, for specific parts and structures. And kind of walk me through what the qualification environment might look like for applying thermoplastic composites in a major aerostructure, whether it's for urban air mobility or maybe even commercial aerospace. What does Solvay see that has to be done? Like, what would be the ideal environment for you to accomplish that? And what are the options or scenarios? Just give us a sense for what that looks like.
Perhaps that's a good question for Trevor. Trevor, do you want to on channel on thermoplastics?
Yeah, I can see from an aerospace perspective, which is more of my background, that there's going to be a lot of test in actual test to back up what's already been simulated. I think especially in today's like UAM and aerospace type environment, I see a little bit, and rightly so, some more conservatism and some very interest in oversight there. So less exception of just the virtual tools out there that I think have really grown a lot with even from the processing and forming standpoint of like, Anaform and LS Dyna, but also on the FEM model integration with that, with, over mold flow and whatnot. We're also, I think, going to have to do a lot more of the actual testing of those parts, which again, the same MSAC center in Brussels has all of those, ability to do the high-speed testing, and also a lot of it, which is usually tied to automotive, but also all of the other testing that's required. And like you mentioned with the NCAMP databases and things like that, I think a lot of this is going to have to be backed up across the way with those prototype tests. I think that'll give a good feel across the industry of matching up the virtual with the actual there, and that'll become, people will be more used to understanding what the outcomes there with the thermoplastic materials are, and the integration of, say, overmolding and other form types, what's to be expected out of that. Go ahead.
I assume that work is going on right now, and it will be going on for several years.
Yep.
Is there a reasonable window that you think, do you think if we have this conversation in 5 or 7 years that you will be substantially through that major testing, and that we will have good qualification data in place that will give us confidence to apply thermoplastic to structures? What kind of timelines do you think it would be reasonable?
Yeah, I think a lot, for like UD tapes, I think a lot of that is already, some is already available. There's more materials coming out, so I think that will be expanding. It's really the other form types that I think are going to be, in the future will begin to be added to that. The fabrics, the braids, the overmolding, that type of knowledge base, I think is a little bit farther out. It's in process, but to generate all that and feel comfortable with what's behind that, especially with industries that are newer into thermoplastic applications, that may take a little longer to assemble all of that type of data. Plus, as you know, your large OEMs, they like to do this internally and on their own as well. So that may be lagging until we have new products coming on from the Boeings and the Airbuses and those types of things.
Do you have any tier ones who are interested in trying to develop some qualification data?
Yeah, so several, the largest tier ones, to the aerospace companies, I think like even, we were talking about Wichita State and IR and whatnot. I mean, Spirit is right next door down there. They supply both Boeing and Airbus, and several others that we talk with that are very interested in exploring different material options in thermoplastic beyond what they've traditionally looked at in the past. So I do believe that interest will continue, and it's growing. I think it would behoove us to have somewhat of a common development, like when the thermoplastic waters rise, all the boats can float a little higher rather than everybody kind of trying to develop things on their own. So I'm hoping there'll be some good collaboration in working in this area going forward. Like we've even seen with the FAA support for, the NCAMP database values for thermoplastics. I see that as a good collaborative effort for the whole industry to take advantage of.
Okay. Well, that's a very hopeful wish you have there. This is an industry that
I'm always positive.
Secret, so.
Yeah.
Okay.
We have for sure still some key technologies like welding, which needs to be progressed a lot further in its qualification preparation.
Yeah.
At Solvay, what we have also as initiative internally, which is essentially is definitely virtual testing. So driving forward the virtual testing capabilities or the prediction capabilities, such as that means no longer just first buy failure, bringing damage progression, damage modeling, also forward, and then using virtual testing and not just physical testing. So that's 5 years from now and forwards, it will be an interesting discussion to see how the industry has progressed on these aspects.
Okay. Next question. My observation is that the evolution of thermoplastic tapes is lagging thermoset tapes for obvious reasons. But we're starting to see thermoplastic tapes deployed in different ways other than just straight UD tapes. So for instance, we're starting to see some braided thermoplastic tapes, or some maybe like to develop some 2D or 3D preforms. And I'm wondering if you're seeing any of that, and what kind of evolution we might expect there in terms of trying to change the format a little bit to make thermoplastic tapes do different things for us and provide different advantages.
Yeah, I think that's a great point, and I feel like that's one thing in composites in general that's a little bit lagging, especially on the thermoplastic side, is designing the right format for the right part. To have the suite of tools and knowledge base to know, okay, if this is the part geometry, this would be the correct format to apply to that, or this would be the correct design. I think some of that maturity is yet to take place, but even like the window frame behind me right here is done out of a braid that within that, a flat braid in this instance, and we'll continue on that. You can imagine it's one of the trickiest geometries. I mean, imagine a hoop with 2 joggles in it. I mean, that's not something that's easy to say stamp form quickly, but as we're looking at rate pressure, you got to be able to form a geometry rapidly, and that's where the braids have really come in to shine there. And there's different types of braids. This one in particular, within each layup, is a quasi-isentropic type layup. So you get very stable and good parts out of that also have that tie through that you wouldn't get from a fabric, that interlock.
Right.
So I'm excited about that. And the different formats there, I think, is going to be a great expansion in looking at what the geometry is, what type of format to apply to that. Same with, I have a frame over here that's done out of a braid. I just realized this morning that I've got probably half my parts behind me are out of braided structures. And as we see more, especially, applications in seats and interiors, like the structure you normally see at the base that happens to be tubular, more tubular structures also in energy transition. So the braids that, initially always start as a tubular type structure. This window frame happens to be a flat braid in the end that gets stamped form, but using even within that, whether it's a tubular braid or flattening that braid out. There's also the UAM is an interesting area where lightweight, they want it very light, and so minimal plies, but they want the most out of what they're using. So like I mentioned, a braid that is quasi-isentropic within that layer, you may only need a couple layers to make whatever that application is, and so it can be very lightweight in that respect.
Are there any other formats or fiber formats that we should keep an eye on that you feel like are ripe for development for thermoplastics? Talked a lot about braiding. Are there any others?
Yeah, along with, so I guess within that, I mean, the fabrics, I mean, the multi, whether it's a 2x2 twill or a 5 harness or an 8, you know, those, and having the data to back those up. Same with the braids, whether it's a quasi-isentropic within one layer or a bimax that has, you know, 45s in there. I think within each one of these, there are multiple options. And so I feel like the knowledge of the, you know, the advantages and disadvantages of each one of those, that maturity needs to come. But those are some of the new formats. I'm not thinking of ones beyond that right now that seem to be missing. It's really within all these different formats, just developing the maturity of the knowledge base so that more people can use them in the right way.
Okay. So before we wrap up, I want to add one more question. Or did you, Johannes, did you want to say something?
There was more, yeah, on the tape use. If you take more the automotive side and overmolding, for example, there the challenge is not necessarily the different product form. Their braid is one of the product, for example, also of interest, given that it's stable, it's mechanically stable against these high injection pressures, and at the same time can be used in very thin configuration, which is always an issue. The challenge there for sure is going, or not the challenge, one of the main points is trying to go away from the classic organo sheets and hence tapes. The challenge for tape, not necessarily just different than tape, a different product form, but make out of tapes local reinforcements, making tailored links, finding approaches, which is not necessarily on the side of the material supplier, more in between on the conversion, but the very efficient use, the minimal use, and highly orientational use of composites for these kind of applications. We see this pushing very much where tapes are key, but at the same time they need to be applied not just in organo sheet form, but in tailored form. Yeah.
Okay. So are you saying the braided format is allows tailoring to be applied more easily and more readily, whereas with UD tapes you've got to have some sort of system that puts the tapes in the right direction, in the right place, in the right, you know, in the right layer to serve that part? Is that what you mean?
It's primarily for thin structures where braids, due to its symmetry and the multidirectionality and the stability, braids coming from tape, but are creating their very thin structures, where the classic tape, either we need to get to very, very thin tape layers to get then again a symmetric behavior, but that comes with costs and challenges in making these tapes in the first place. So their braids are really an interesting intermediate product form.
Okay. So before we wrap up, I have one quick question. I wanted to circle back to the urban air mobility market. When we think about applying thermoplastics on an urban air mobility aircraft, are there structures that you consider ripe for first application? Like when we see thermoplastics first show up on an UAM craft, where do you think what parts do you think we're going to see those on first? What would be good targets for that?
I think wing structures are excellent, and in this size, you know, UAM and even in drones, I mean, your wing sizes are much smaller than traditional aerospace. So, but the structures inside of them tend to be more traditional than what we've seen previously. And so, if designed correctly, even with like a spar, they don't tend to have all of this curvature in there. If designed properly, could be from a CCM type of a C-channel process, a continuous compression molded type C-channel. And then, as we look at ribs, those are classic opportunities for thermoplastics to be stamp formed. So those and all of the interiors and bracketry and all of those types of things, I think are very comfortable, already done in aerospace type of structures as well. It's when we jump to the everything everywhere in thermoplastic, that's where I back out a little bit, and it's like, let's look at what is the I mean, there's the advantage of welding there, but really let's look at what is a good base to start from and look at what's the right material for the right application.
Okay. Great. Well, Trevor and Johannes and Jim, I want to thank you for joining me here on CW Training, these great comments and insights. And we'll have to revisit in a few years and see how all of this is unfolding.
Absolutely.
See how our crystal balls turned out. Yes.
Yes. Yeah. I'm sure we're all right, spot on. All right. Well, thank you very much. I appreciate you joining me today. Have a good day.
Thank you.
Thank you.
Thanks a lot.